angles inside and outside of the circle. The first angle we're going to look at, our first angle type, is what we call a central angle. And a central angle is formed by two radii. So let's call this center point A, this intersection point B, and this intersection point here C, and we'll label this angle angle 1. So a central angle is an angle formed by two radii, and the vertex is at the center of the circle. And here's what we know is true about that angle measure. It is equal to the measure of the intercepted arc for that angle. What do we mean by intercepted arc? Well, you see when we extend the radius from A to B or from A to C, there is an arc that we can connect from B to C, and that is what we call the intercepted arc for angle 1. And the measure of the arc is equal to the measure of the central angle, and you can think of it as the percentage of the full revolution that is accounted for angle 1 is equivalent to the percentage of the full circumference accounted for an arc BC, which is why they're equivalent in measure. Okay? So we're going to say that for this picture, angle 1, the measure of angle 1 is equal to the measure of intercepted arc BC. So that is what's true about central angles. So we'll say they equal the measure of the intercepted arc related to that angle. Now, there's two different types of arcs that we want to be aware of on the circle. There's a minor arc and a major arc. So arc BC, you may be wondering, well, why didn't we go this way? Because that's an arc from B to C as well. Well, the one I have in blue is what we're going to call a minor arc. It takes up half, or less, I should say, it's less than half of the circle. A major arc is going to be more than half. Okay? And exactly half we'll call the semicircle. So how do we distinguish between the minor arc and the major arc? The minor arc is going to be using two letters to label it. And the major arc is going to be using 3. So let's say I introduce another point, D, over here. We know that if we see BC versus BDC, BC, 2 letters, this is the minor arc. 3 letters, we know we're dealing with the major arc. And that's how you distinguish between the two. And you can see that major arc should be equivalent to the measure of this angle, called angle 2, that is on the other side of angle 1. And that is still a central angle. It's still formed by 2 radii. So arc notation, 2 letters minor, 3 letters major. What is a central angle? We know it's equivalent to the measure of the intercepted arc. That's a piece that's going to become very important for the next type of angle we're going to look at. Which is what we call an inscribed angle. And an inscribed angle is formed by 2 chords where the vertex of the angle is on the circle, okay? So this is what we'll call this point of intersection of the vertex for this angle A, B, C. We'll call this angle 1. So this is what we have, an inscribed angle. And it's formed by 2 chords. And the vertex is on the circle. So why is that important? Because I could introduce another chord, and you could say, well, here's an angle formed in here, and those are 2 chords, so is that inscribed? The answer is no, because this vertex point does not fall on the circle, okay? So vertex has to be on the circle for the inscribed angle must be formed by two chords. And what we want to know is how does it relate to its intercepted arc? So the central angle was equal to the measure of the intercepted arc. How does the inscribed angle relate? Well, here's what we're going to do. We're going to introduce our center point. We know that the central angle related to BC, should be formed by the two radii, are equal. So we know, let's call this angle 2. The measure of angle 2 is equal to the measure of arc BC. So we know that from our central angle. So how does the measure of angle 1 relate to arc BC? Well, here's what we're going to do. We're going to introduce a diameter. Actually, let me do that in a different color. That extends from point A and passes through our center. And here's why we are going to do that. We know that the distance from the center to a point on the circle is always the same length. So let's call this point the center point D. We know AD and BD are the same. We also know that AD and DC are the same. Now, what does that do for us? Well, let's imagine this angle 1 just got split by that diameter, as we can see. So let's call this little sub-angle, angle 3 and angle 4. And angle 2 got split as well into angle 5 and angle 6. So what we know is the measure of angle 1 should be equal to the measure of angle 3 plus the measure of angle 4 from the split. Right? That's our angle addition postulate. The sum of two parts equals the whole in this case. We also know that the measure of angle 2 is going to be equal to the measure of angle 5 plus the measure of angle 6. Now, why did we introduce that line, and why did I bring up the fact that those radii are equal in those certain scenarios? Well, when I marked off those tick marks to show that the radius is equal, we can also see that when I introduced that red line, a couple triangles were formed. And both triangles, in fact, are isosceles. And we know base angles of isosceles triangles are congruent. So if that below is angle 3, then this angle up here is also angle 3. And angle 4, this should also be angle 4 because of isosceles triangle relationships. And what we also know is that when I extended through that center point, from A through D. The reason why I kept going and didn't stop at D, I could have, but what happened was I created this scenario here where I have, say, 3, 3, and this angle 5. That angle 5, if I'm just looking at that piece, represents an exterior angle on that isosceles triangle. And we know that the sum of remote interior angles is equal to an exterior angle. So we can also make this conclusion that angle 5 the measure of angle 3 plus the measure of angle 3, which is 2 times the measure of angle 3. And that same reasoning could be used to relate angle 4 and angle 6. Angle 6 is an exterior angle on that isosceles triangle with base angles labeled 4. So we can say the measure of angle 6 is equal to 2 times the measure of angle 4. Now remember, our goal is to figure out what's the relationship for angle 1. So we can say that the measure of angle 3 is half the measure of angle 5, and the measure of angle 4 is half the measure of angle 6 by manipulating these two. And then I can make a substitution into my equation that measures the angle 1. So we can say the measure of angle 1. We know the measure of angle 3 is half the measure of angle 5. Plus angle 4 is half the measure of angle 6. Now, why do I want to do that? Because now I can say this. The measure of angle 1 should be measure of angle 5 plus the measure of angle 6 all over 2. But what's 5 plus 6? That's 2. So we can say the measure of angle 1 is equal to the measure of angle 2 over 2. And our goal is to figure out how does measure of angle 1 relate to its intercepted arc BC? Well, the measure of angle 2 is equal to the measure of arc BC. So we can say the measure of angle 1 should be equal to half the measure of arc BC. And there is your proof as to why an inscribed angle is half the measure of its intercepted arc. So that's what we're going to take away from this whole thing. So if you know the measure of an inscribed angle, you know the intercepted arc is double that. So let's say angle BAC was 30, arc BC should be 60. If you know the measure of the arc, the inscribed angle is half. So if you see BC is 60, then you can say the angle that's inscribed related to that is 30. Whereas the central angle would be equivalent, equal to 60. So know the difference between inscribed versus central and how they relate to the measures of their intercepted arcs. So far we've introduced an angle formed by 2 radii and an angle formed by 2 chords. Let's look at another interesting scenario where we could have 2 secant lines meet at an exterior point. We want to know how they relate to some intercepted arcs. So what are the intercepted arcs we're dealing with here? We have AE and BD. Those are the arcs related to that angle that's formed by these 2 secant lines that are meeting out here. So how are we going to figure this one out? Because we want to figure out the relationship between that angle C on the exterior and its arcs AE and BD. And all we know so far is relationships with central angles and inscribed angles. So here's what we're going to do. We're going to introduce our own chord. And time again, you will see that introducing your own lines in circle problems often give you a valuable piece of information to reach a conclusion that is desired. So when I introduce the chord from A to D, what we now have is this angle 1. And angle 1 is an inscribed angle. I can see it's formed by 2 chords, AB and AD, and its vertex is on the circle. And I know that angle 1 is equal to half the measure of arc BD. Or let's just call it BD over 2. And by introducing the chord AD, maybe you can see that there's another angle here that's also inscribed with chord AD and DE, and it's related to arc AE. Now here's the other cool thing. By introducing that chord, we have this triangle, ACD. Should probably draw that a little better. So from A to C to D, there's a triangle formed. And that angle 2 serves as an exterior angle to that triangle. And therefore I know the sum of the remote interior angles should be this, when I add them together, the sum of those remote interior will equal the measure of the exterior angle. So we know that the measure of angle 2 should equal the measure of angle 1 plus the measure of angle C. Now, we want to know the relationship between C and those arcs. And we know how 1 and 2 relate to the arcs that we're interested in. So we can make a substitution. We can say the measure of arc AE over 2, which is equivalent to 2, should equal the measure of BD arc over 2, which is equivalent to the measure of angle 1, plus the measure of angle C. So now I have an equation that relates the three things that we wanted or that were of interest to us. So I can see that the measure of angle C is equal to the measure of AE minus the measure of BD, all divided by 2 when I manipulate that equation. So if we have two secant lines that meet at a common exterior point, we know that the measure of that angle out there is equal to larger intercepted arc minus smaller intercepted arc divided by 2. And how did we figure that out? By introducing our own chord, knowing the relationships between arcs and intercepted and inscribed angles, and identifying triangle relationships once again. So understanding triangles never goes away. Huge part of high school geometry. So there's some relationships between angles inside and outside of the circle. And before we conclude the video, let's look at one last example, which is really just a special case scenario of something we've already talked about. Here's my center point. Let's say I draw in a diameter and I inscribe an angle with two chords where the chords intersect at the end points of this diameter. It forms A, B, C. So what do we know about the measure of this angle in here? Well, we see that's an inscribed angle, and the arc that it's associated with is a semicircle, right? It's half the circle. We know it's half the circle because it's related to that central angle. That central angle is formed by the diameter. So we know diameter is 2 radii, right? We've talked about that before. So radius, radius. That means this is a central angle in here, and that central angle is equal to whatever the measure of that arc is, and halfway around is 180 degrees. And it makes sense because we have a straight angle, and we know straight angles are 180 degrees as well. So we can see when we have a diameter, its measure is 180 degrees, the arc is 180 degrees that is intercepted for that. So that should all make sense. Now, what do we know about that original angle we were looking at? Well, it should be half the measure of the intercepted arc related to it, in which case that would make this a right angle, and now we have a right triangle with the two chords and the diameter. So something you want to pay attention to is when you have an an inscribed angle formed by two chords where the intercepted arc is a semicircle, you can form a right triangle because you know the semicircle is 180 degrees. Therefore, the inscribed angle is 90 degrees. And if I draw a chord that connects A to B, it will pass through the center, which will represent a diameter, and now you have a right triangle. So that's just one of those special cases for an inscribed angle that you want to be on the lookout for. So that will conclude the video on angles inside and outside of the circle.